in the subset distinct. Okay, so this is a generalization of, maybe you've heard in combinatorics this question of what is the largest subset of 1 up to 1,000, which is free of arithmetic progressions. Yeah, there's a very classic problem in extremal combinatorics and also related, to things like Green-Tau theorem and these like very interesting things in extremal combinatorics. This is a 2D variant of this. Okay. And I just want to advertise this as a kind of benchmark of techniques. So so Adam has kind of done some really beautiful stuff on this, and then we joined forces with François and Jordan, and I just think that this is a great benchmark problem. So we've tried this problem with some kind of local search and transformers, and gotten somewhere. So we have a good, and also we've used stat solvers for small values of n. So up to about n equals 30 or something, we have a list of the best constructions. But then for n equals 100 or something, we have these very interesting, very large constructions. And so the first problem is to try a range of techniques on this specific problem. The other thing that I really like about this problem is it's like essentially trivial to code. There's not a big data generation kind of bottleneck. Okay, problem number 1. Problem number 2, so that's 1. Problem number 2 is searching for interesting Jones polynomials. So you probably know that to a knot in S3, you can associate, so this is why what? You can associate this Jones polynomial, which is a Lorentz polynomial in Q and Q inverse. And it's a very well-known open problem as to whether this Jones polynomial detects whether you're an unknot or not. And I think like an ambitious program is to like actually try to disprove that conjecture. But I think that like one interesting intermediate is, can one search for like very unusual looking Jones polynomials? So Jones polynomials, for example, with very small coefficients or something. And I've been working on this problem from the point of view of the Braid group with Ashmi, François, and Oded Jacobi. But the idea of this project would be to take a different approach. And so in that approach, we really kind of use the fact that a knot is the closure of a braid and kind of search in braid space. But I think it would be very interesting to perform this search directly in kind of knot space. And I have various ideas how to go about that.
Just as a comment, I'm also looking at this actually from using some contrastive generally.
Okay.
So specifically Jones polynomial.
Okay.
Okay.
Yeah, excellent, thanks.
How does reinforcement work?
Yeah, so one thing that we've had a lot of luck with is just using a transformer to slowly guide search. So let's say I generate, in some scheme, I generate 1 million knots, and then I evaluate the Jones polynomial. And I have some measure of unusualness. So one of the things might be just some of the norms of the coefficients, for example. And then I take the constructions in my symbolic language, which lead to the lowest, the most unusual knots. And then I retrain then I train a transformer based on that, and then resample. And so this is a very gentle way of pushing a distribution into unusual terrain. Okay. So, typically you think, oh, I'll just like go after this, and then you try, and what happens in my experience is it collapses too quickly. Whereas this approach is very nice because it kind of keeps a kind of open mind about what's out there, but slowly pushes it into, potentially interesting areas of the search space.
But this is predicated on believing that a Jones polynomial not a trivial transform is near enough with small transform. There's some kind of continuity.
Absolutely. It's predicated on that assumption.
Okay, great, thanks.
Any else further questions? Or should we-
Well, we'll come back to it. I'd like to get like, maybe problems up on the board, and then of course we'll come back to them and discuss some more. Please.
Hi, right here.
Yes.
And so now.
We'll leave it
Pretty-
unless we need to space. Yeah, you can start.
Sorry, I want to consider Kronecker coefficients. So what are these coefficients? The symmetric group, and then consider irreducible representation. Then lambda is a partition of n. Okay, so an irreducible representation is parameterized by a partition of n. And then we take the tensor product. Then we can, of course, decompose it. Okay, then this coefficient is called the Kronecker coefficient. And the problem is that people in representation theory and combinatory, algebraic combinatorics have been studying these coefficients, but their goal was to obtain combinatorial description of these coefficients. Because for literally Richardson coefficients, we have a complete description combinatorially. But for like 80 years, no progress. And then it turned out that determining whether these coefficients are 0 or non-zero, this is already NP-powered. So it's definitely a difficult problem. Then I used some machine learning technique. So I considered this as a 3n-dimensional vector. So if it is necessary, you put 0, then. And then from the set, I did a classification problem. So 1 means it's non-zero. And then the result was very good. So if I use CNN or light GBM, then I obtain the accuracy of 96 to 98% of accuracy. So this is very good. But now the next question is the feature analysis or salience analysis or the attribute analysis, whatever the name may be. So the next task is I'm proposing is salience analysis, and then see why or how this works. I did some PCA. And then got some results, our corner PCA. But probably if we are interested, then I can explain the results. But my method was PCA, and then I got something new. And then it gave me and probably other people new perspectives. In any case, this is missing. And then if we consider what Zordi and DeepMind people did, then this is the natural next step. But this is not happening.
Thanks. No problem. Okay, there's two more. Okay, so whoever wants to go first, go ahead.
I can say a few more things about the problem I discussed earlier, I outlined.
Okay, there's, so who was speaking?
Petros.
Petros, okay. Why don't we, come back to you? So we'll have to,
Okay.
we get the slides available and then maybe we can come back after these two.
Right, so this problem is something which,
Did you want to use slides or you're good?
I mean, perhaps maybe I can.
Because if I'm going to set up slides, so you didn't want to use slides, and so do you want to come up and use your board and then I'll put it on the screen?
I think it doesn't make it.
And then
I mean,
try to bring that to screen.
Should right on the left or the right side.
Oh, I think it's all within view, just.
Oh, okay.
It's something.
But Mike, erase me,
What's that?
erase my side.
No, I don't think we need to do that.
We don't have to.
So, I wanted to mention a problem that I have some experience with, but I'm certainly not working on it now, but I'd be very happy to interact with someone who does want to work on it, because I know a little bit about the history and motivation, and it's about the unknotting question. So this has to do with loops of string in 3-space, which are unknotted, but not obviously unknotted. So the question is, how can you tell? So maybe it's nice to have a picture on it. For the same time, I only drew half the unknot. I drew an unknotted arc in half space, but the picture that I would draw for 5-minute talk would be the mirror image on here as well. And this is the unknot. As you can see by, for example, whatever's over on this side, you could take this little bite, sailor might call it, and stretch it out and pull it over the right-hand side, and then everything goes away. So it's the unknot, but notice that a greedy algorithm won't work to discover it's the unknot, because as you pull this bite over, there'll be lots of additional crossings. So the total number of crossings will go up before it goes down. So you're sort of stuck in some kind of local minimum. And 30 years ago, there were extensive numerical experiments at the Geometry Center in Minnesota, where they looked at this energy functional. It's a double integral over S and T, where gamma is parameterizing the knot. And it's the norm of the derivative of the 2 points S and T in the numerator. So this just gives basically the measure, the S and T. The crucial thing is the denominator. It's a power of the difference. The second power that gives a conformally invariant functional. So the point is, if gamma, say from the circle into 3-space, parameterizes the knot, then this thing in the numerator is just the density of pairs of points along the knot. And what the functional is you consider all pairs of points, and it's sort of an energy, sort of a potential energy, which is 1 over r squared. It's sort of like a potential energy as if you were in 4 dimensions for some reason. Square is important to get a nice conformally invariant functional. And this needs a little bit of regularization, this integral, because there's sort of an obvious blow up as points come together on the diagonal, but that's easy to remove by just comparison with the round circle. So regularization of this, so it's an unknown question whether this functional has any additional critical points when applied to unknots. You would think it would be a miracle if it didn't, if this thing unknots. But this is a classical approach to unknotting. There are probably better AI approaches or hybridizations with the integral in AI. I will say that people thinking about 4-dimensional topology, the Poincare conjecture, for example, recently papers of Lisa Piccirillo and Cyprian Montelescu, relate finding counterexamples to the Poincare conjecture to discovering that certain knots are slice or ribbon. This has to do with their ability to be spanned by certain disks in the four-wall. And the unknot, of course, is the easiest thing to span because it just has an embedded disk even in three space. But it turns out these more subtle properties of slice or ribbon, which I won't define, can be explored if you have a good algorithm for detecting unknots. If you can detect unknots, then there are certain moves you can make called ribbon moves. And then you look at the pieces after you do this and you ask whether you've gotten an unknot or an unlink. That's how you decide if your knot is ribbon, a slightly more sophisticated algorithm for slice. So if you did have good results in detecting unknots, that could be used as a submodule in lots of interesting problems in four-manifold topology.
Great. Thanks. Okay, so we'll come back and discuss more. Why don't you start setting up? And while you do that, I have to bring the screen down. Can we get volunteers, as I said, to write down somebody's problems, one for each problem, if somebody volunteered for the isosceles three subsets, and then of course you can easily do it for somebody else too. Right, yes. Okay, number two. We have a volunteer to put a description on the Zulip. You also volunteer for that. I mean, it's of course that's great. Okay, Kronecker coefficients. You may require, okay, you're on that, that's very natural. Okay, the anotic problem that the approach that Mike Friedman just described. Okay, great, excellent. Okay.